We're going to look at the final exam review for solving systems of equations. The three major methods for solving a system of equations are graphing, substitution, and elimination. And then the only other thing beyond that would be systems of linear inequalities, which we would solve by graphing. So looking at the first few problems, we're asked to find the solution to the system by graphing. Just a reminder, the solution to a system of equations is the ordered pair where the two, either graphically where the two lines would cross, or algebraically the ordered pair or the values that make both or all equations in the system true. So looking at number one, I want to graph both of those lines. What I should notice is neither line is in slope-intercept form, so I'd first want to do that. So I'm going to rewrite the first equation just off to the side here. So to get it in slope-intercept form, I'm going to have to subtract x from both sides. I'm looking to get y by itself. So I get 2y equals negative x plus 4, and then divide everything by 2. So what I end up with is y equals negative 1/2 x plus 2, and that is the equation I'm going to graph. I'm going to do the same thing for the second equation, so I would subtract x from both sides. So I get negative 3y equals negative x minus 6, divide everything by negative 3. I'm going to write it off to the side here. What I should get is y equals 1/3 x plus 2. So I have two different equations. All I've done is kind of rewritten them in a form that's easy to graph, and now I'm just going to graph them and see if and where they intersect. So if I graph that one in purple there, so I go to my y-intercept at 2, and my slope is up 1 over 3. So my advice would be plot that point as many times as it fits on your grid, just so you can kind of see the path of that line and then connect it. If I draw the line that's in red there, go to 2 as my intercept, but it has a negative 1/2 slope, so I go down 1, right 2, down 1, right 2, and what you'll see is they intersect at the y-axis actually, which is the point 0, 2. The way we write our answer to a system is the ordered pair where they intersect, if it's a graph, or the ordered pair that makes both of them work. So in this case, it's 0, 2. For number 2, I'm going to do a similar process. I'm going to make sure they're both in slope-intercept form, and if they are, once they are, then I will graph them and see where they cross. So the first equation is already in slope-intercept form, but the second equation is not, so I'm going to get y by itself. So first subtract 2x from both sides. And then I'm going to have to divide everything by negative 3, whatever's in front of the y. So what I end up with is y equals positive 2/3 x plus 3. So here are my two equations. First one's already in a form I recognize. The second one now is. I'm going to graph them. So if I graph the first one, the slope is negative 1, and the intercept is negative 2. So I put a line, or across the y-axis at negative 2, and then draw my slope down 1, right 1, down 1, right 1, down 1, right 1, and connect it with a line. So there's my graph, and then the line that's in purple, I start at positive 3 and then go up 2, right 3, up 2, right 3, and there would be my line. So drawing both lines, they intersect at a nice integer point, and that point is the coordinate negative 3, positive 1. Number 3, I'm going to handle it very similarly, get them both in slope-intercept form, and then graph and see where they intersect. So first, I'm going to subtract x from both sides, and I get y equals negative x plus 5, and that's actually it. There's no coefficient on y that needs to be divided, so that's already solved for. Second equation, I'm going to do something similar. So I get 2y equals negative x plus 6. Then I'm going to have to divide everything by 2, so I'd get y equals negative 1/2 x plus 3. And now I have two lines that I can draw and see if and where they intersect. So I'm going to graph that purple one first, go to positive 3 as my y-intercept, and then slope would be down 1, right 2, down 1, right 2, down 1, right 2. So there's my line. Connect those points with a line, and then the second equation is positive 5 as my y-intercept, and then the slope is negative 1. So down 1, right 1, down 1, right 1, down 1, right 1. And if I connect all those points with a line as far as it'll reach, what I see is they intersect at the point 4, 1, and there would be my solution. Number 4 kind of has a lot going on. You'll see both of those equations, neither of them are in slope-intercept form, so I'm going to kind of walk through the process there. So the first one, I'm just going to rewrite the equation, and then I'm trying to get y by itself. So subtract 3x from both sides. What I get is negative 5y equals negative 3x minus 30. And then you divide by whatever's in front of your y, which in this case is negative 5. And then I'd get y equals 3/5 x plus 6. So that would be the first equation I'm going to end up drawing. And then I'm going to do the same thing for the second equation. So subtract x from both sides. So I'd get negative 5y equals negative x minus 20. Divide everything by negative 5. So I would get y equals positive 1/5 x plus 4. So now I have two equations that I can graph. So I'm going to graph the first one here in red. So go to positive 4. My slope would be 1/5, up 1, right 5, up 1, right 5. Or down 1, left 5, down 1, left 5. There's my line. Then graph the second one. Go to positive 6. Go up 3, right 5, or down 3, left 5. There would be my line. And what I should see is the intersection point at negative 5, positive 3. And that would be the process of solving a system of equations by graphing. The next method for solving systems of equations that we're going to talk about is substitution. The reason it's called substitution is we're going to take an equation that's in two variables and substitute for one of the variables so that it becomes an equation I can solve. And the goal there would be, in order to use substitution, is one of my variables should already be by itself in one of my equations. What I mean by that is if you look at the second equation in number 5, you'll see that I have y equals. So what I can do is take what y is, which is 4x plus 6, and replace that with the y in the first equation. That's why it's called substitution. So what I like to do is just rewrite that first equation, but where y was, I would put what y is equal to in a set of parentheses. Definitely have to put that in parentheses, otherwise you'll potentially make a mistake when you multiply, but that's the whole substitution part, replacing a variable with another expression so that I can solve it. If you notice what we have left, that's an equation that we've talked about solving before. What you'd need to do there is just distribute that negative 5, so you'd get 2x minus 20x minus 30 equals negative 12, and then I'm going to combine like terms as much as possible on the same side, so I have that 2x minus 20x, which is negative 18x, and keep the rest exactly the same. And then I want to actually solve for x, so I would add 30 to both sides, and I'd get negative 18x equals 18, and then divide both sides by negative 18. So what I have is x is negative 1. So that is part of my answer. If you remember from the previous examples, we had solving a system by graphing, and our answer was an ordered pair, x and y. Our answer for these is still an ordered pair. The only difference is we have to actually do the solving by hand, right? I have to take this negative 1 and somehow find a y value. The easiest place to go will be actually take that equation where y was by itself and replace the x in there with negative 1. Because y is already solved, I can literally just say 4 times negative 1, which is negative 4 plus 6, so y has got to be 2. So my answer, please make sure you put it in the correct order, x then y, should be negative 1, positive 2. So that's kind of the substitution process. One of my variables was already isolated in one of my equations, so that's what I'm going to take and replace with something in my other equation. So number 6 I'm going to handle very similarly. The only difference is you'll notice x is by itself, so x equals 2y minus 5, so I'm going to take that and put it in place of the x in the first equation. So that's what I'm going to write. Take that top equation as is, except replace x with what x is equal to. And then distribute, combine like terms, and solve. So I would distribute that negative 3, so I get negative 6y plus 15 plus 5y equals 11. Then I would combine like terms, so I have a negative 6y plus 5y, which is negative y plus 15 equals 11. And then get y by itself. So subtract 15 from both sides, so I get negative y equals negative 4, and then to get positive y by itself, I would just divide both sides by negative 1, so what I should get for y is 4. And again, that's only half of my ordered pair. I need to somehow find my x value. The easiest place to go would be where x was by itself, and just replace the y with what I found y to be. So x is going to be 2 times 4, which is my y value, minus 5. So x is going to be 8 minus 5, which is 3. So my answer should be 3, 4. Number 7 and 8, I'm already in a form that I can use substitution. One of my variables is already isolated, so I'm going to take the negative 4y minus 4 and replace it with the x in the first equation. So that's what I wrote here. Then I'm going to distribute. So distribute that, I get negative 12y minus 12 plus 2y equals 8. Combine like terms, I have a negative 2y and a positive, negative 12y and a positive 2y on the same side, so those combine to be negative 10y. Minus 12 equals 8. Add 12 to both sides, and then divide both sides by negative 10. So what I should get for my y value is negative 2, and then to go back and find my x value, I just replace that with a y in one of my equations. The place I would go is where x was already by itself. That would be the easiest. So I'd get negative 4 times negative 2, which is positive 8, minus 4 is 4, so I get x is 4, y is negative 2. Please be careful that you write that in the correct order. And then 8, handled very similarly to number 7. Replace 6y minus 19 for the x in the first equation in parentheses. Then I'm going to distribute. So now that I have 7y distributed through that binomial, now I'm going to combine like terms. So 42y and 4y is 46y. And then everything else stays the same. Then I'm going to solve for y. So add 133 to both sides. So I get 46y equals 138. Divide both sides by 46. Y is going to be 3. So now I have my y value. I need to find x. So I'm going to go up to that first set of equations and replace the y with 3. So x is going to be 6 times 3 is 18 minus 19, which is negative 1. So my answer should be negative 1, positive 3. And that's kind of the process of solving systems by substitution. The goal would be to have an equation where one variable is already isolated. Then I use that to substitute in my second equation. The third method for solving a system of equations is what we call linear combinations, or addition or subtraction, depending on how it's been taught to you. So what we're looking for here is that both equations are in the same form, meaning x's are vertically aligned, y's are vertically aligned, and my constants are on the other side. So that's true of all these equations are already all lined up. But why it's called linear combinations, we're essentially combining the two equations to get one of the variables to eliminate. That's just why it's sometimes called elimination. So what we're looking for is we're looking for the coefficients of our variables to be something that can add or subtract to eliminate. So what I mean by that is if you look at the y coefficients in the first problem, number 9, you'll see we have a positive 2y and a negative 2y. So if I were to combine these two linear equations with addition, so if I added the system together, what would happen is the x's would, negative 7x plus 10x is 3x. The y's would eliminate, they'd add to 0, which is what we want. So now we end up with an equation with just x. So we get 3x equals, and then negative 5 plus 8 is 3. So we end up with the equation 3x equals 3. Divide both sides by 3, x equals 1. Again, the reason why that works is only when we have the coefficients of one of our variables that are set up so that if I added them or subtracted them, they would eliminate. So that was already the case for number 9. So now that I have my x value, I need to take that and find y, which means I need to replace x in one of my original equations with 1 and then solve for y. The equation I'm going to use is actually the top equation. So that same equation, exactly how it was, the only difference is I replaced x with 1, so you should get negative 7 plus 2y equals negative 5. If you solve that equation, you should end up with your solution for 9, or solution for y, which is part of our answer for number 9. So add 7 to both sides. So 2y is 2, divide by 2, y is 1. So my final answer for number 9 is 1, 1. Similarly for number 10, what I'm looking for is to get one of the variables to eliminate, and what I'm looking for to do that is the coefficients of the variables. So if I look at my x variables, one of the coefficients is 3, one of the coefficients is 2. If I add or subtract those, they don't add to 0. And if I look at the y coefficients, if one's negative 5, one's 3, if I add or subtract those, they don't add to 0. So the system is not ready for me to try and eliminate using linear combinations. But what I can do, though, is multiply one or both equations by something to get the coefficients to match up. So what I'm going to do in this case is multiply the top equation by 3 and the bottom equation by 5. I'm going to do that, and then we'll talk about why I chose that. So multiply everything by 3, I get 9x minus 15y equals 42. Multiply the bottom equation by 5, I get 10x plus 15y equals 15. And the reason why I chose 5 and 3 is because now if you look at your y coefficients, one is negative 15y and one is positive 15y. Therefore, if I add the system together, my y variables would drop out or eliminate. That's the whole point. So I end up with 19x equals 57. And then if I divide both sides by 19, I should get 3 for x. Now that I have my x value, I need to find my y value by taking that x value 3 and substituting it in for one of my x's. So I'm actually going to use the bottom equation. So 2 times 3 plus 3y is 3. All I've done is replaced x with 3, and then now I need to solve for y. So subtract 6 from both sides. 3y is negative 3. Divide both sides by 3y is negative 1. So my answer should be the ordered pair 3, negative 1. All right, for number 11, we're going to look to eliminate one of the variables using linear combinations. Looking at the coefficients of x, I have a 1 and a 3. They're not ready to go for elimination. But if I look at the y coefficients, I have a 1 and a 1. So as is, that system is actually in a good spot, meaning if I subtracted the system together, y minus y is 0, which works out. So what I have to be careful here is I really have 1x minus 3x, which is negative 2x, and then I have 3 minus 1 for the constant part. So what I end up with is negative 2x equals 2, divide both sides by negative 2, and I get x equals negative 1. So now that I have my x value, I need to find my y value. You can pick whichever original equation you want. So I'm going to use the top equation. So put negative 1 in place of x. So I have negative 1 plus y is 3. Add 1 to both sides, and I get y is 4. So my answer is the ordered pair negative 1, 4. That's solving by linear combinations. Again, number 12, I want to try the same process. And I'm going to look at the coefficients of x. I have a 2 and a 4. The adding or subtracting right now wouldn't really work out. And my y's, I have a 1 and a negative 4. So either way, I'm not ready to go for linear combinations. So what I'm going to do is have to multiply one or both equations by something to get the coefficients to match up. So what I decided to do was make the x's match up. So what I did is multiply the top equation by negative 2. And the only reason I multiplied by a negative 2 is because if you look at the coefficients of x now, one's a negative 4, one's a positive 4, so I can add to eliminate. So if I add the system together, I should get negative 6y equals negative 6, and the x is negative 4x plus 4x add to 0. That's the whole point. So if I divide both sides by negative 6, I should get y is 1. Now that I have y, I'm going to put that somewhere in one of my original equations and solve. I'm going to use the bottom equation. It won't matter. 4x minus 4 times 1 is 0. So I get 4x minus 4 is 0, add 4 to both sides, and then divide by 4. So I should get x is 1. So my answer should be the ordered pair 1, 1. So again, linear combinations, we want to make sure the coefficients match up, and if they don't, we might need to multiply one or both equations by something to get them to match up so that I can get one of the variables to drop out. All right, for 13 and 14, we're still dealing with a system, but we're dealing with a system of linear inequalities. The difference there is we're going to graph them much like we would an equation, but we have to consider that inequalities have some shading on one side of the line or the other, and really the reason why is the shaded region on either side of the line really just shows that there are a bunch of other points not on the line that also work for the equation or the inequality. So we're going to graph them much like an equation to start, and then consider how the inequality differs from that. So if I look at the first one, it's already in slope-intercept form. So it has an intercept of positive 1 and a slope of 3/2. So I'd go to positive 1, go up 3 over 2, up 3 over 2, up 3 over 2. And then what we have to consider before we draw a line is remember if there's a difference between the type of line that should be there, a dotted line or a solid line. So if we have strictly greater than or strictly less than, not less than or equal to or greater than or equal to, then there isn't it's not a solid line. And all that means is the points on the line are there as a boundary but don't actually work for the inequality. So that's all that the dotted line means. And then I have to figure out which side of the line to shade. You can try and memorize like which way the symbol means for shading. The easiest way I think is to pick a point not on the line and then plug it into the inequality. So the easiest point to pick is 0, 0. So if I plug 0, 0 in, plug 0 for y, 0 for x, and see if it's true. So what I get is 0 greater than 1. It's not true. So you can see the work there. I just plug 0 in and it's simplified each side. Because 0, 0 doesn't work, that means the side of the line that has 0, 0 on it doesn't work. So the whole side with 0, 0 doesn't work, so I would shade the other side. So that's how I would handle that. So there's the shading there for that inequality. So graph the line, determine if it's dotted or solid, and then shade it. And then I'm going to use different colors, but for you on a piece of paper, right, I would just shade that very, very lightly because the goal is to see where the two shaded regions overlap. And then I'm going to graph the second one. So I'm going to have an intercept of negative 1 and a slope of negative 1/4. And then this will also be a dotted line that connects those points, so I'll draw that there. And then I'm going to figure out which side of the line to shade by checking a point. Now 0, 0 is not on the line, so I can plug that one in. And the reason I say not on the line is because if I plug the point on the line, I already know whether that works or not because of the dotted or solid line. So the points on the line don't actually work. So if 0, 0 ever falls on the line, then I got to pick something else. So then check 0, 0, so plug it in for x and y. And what I end up with is 0 less than -1, and that is not true, which means I shade the side of the line that doesn't have 0, 0 in it, which is the one below. So I'm going to shade that lightly in green. And then what you'll see is the overlap of the two shaded regions is what I'm going to darken up here. So the way we show the solution to the inequality system is just the overlap of the two shaded regions, and that would be our answer. For number 14, these are what we would kind of call a special case of a line, either a horizontal or a vertical line. The way I remember is x is always a vertical line, because to draw a vertical line I go right or left first, and that would be a vertical direction if I connected that with a line, and y would be horizontal. So I'm going to draw my vertical line first. So I go to +2 on the x-axis and draw a vertical line. And that vertical line should be solid because it's greater than or equal to. And then the shading, you can check 0, 0, but again, we only have x and or y. We don't have both. The easiest way is to really just think about, I want all the x values bigger than 2, which has got to be to the right of it. So I shade to the right. Horizontal line at 5, so I'd go to 5 and draw a horizontal line. The line should also be solid. And then I want all the y values less than or equal to 5, so I should shade below it. So I'm going to do that. And then the goal is to see where the two shaded regions overlap, which is here, which I darken up in this blue here. So that's how we would show the answer to that system. For the next problem here, it's very similar, right? Still a system of linear inequalities. The first one's already in slope-intercept form. The second equation is not. So what I'm going to do is get the second one in slope-intercept form after I graph the first one. So to graph the first line, I'd go to +2, then go up 1 over 5, up 1 over 5. Determine if it's a dotted or solid line to connect them. Should be solid. And then I got to figure out which side to shade. So because 0, 0 is not on the line, I'll plug that in. So I put 0, 0 in. What I'd end up with is the expression is 0 less than or equal to 2. And yes, that's true, which means I shade the side of the line that has 0, 0 in it. So again, I'm using colors, but if not, shade very lightly and then just darken up where they overlap. So that's the first one. The second one, however, is not in slope-intercept form, so the easiest way is, in my opinion, just to add y to both sides. So what that ends up giving me is 3x is greater than y, which I can reverse the inequality and write as y is less than 3x. So now that I have that in slope-intercept form, I'm going to graph that. Now notice there isn't a number added or subtracted after the x term, which means the intercept is 0. So it goes through the origin, then I go up 3 over 1 and draw my line. The line should be dotted because the symbol doesn't include an equal to. Now to pick a point to check, 0, 0 is not going to be a good point to check here because 0, 0 is on the line. So I pick another point. The other easiest one to check would probably be 1, 1. So I plug 1, 1 in there. I would get 1 less than 3 times 1. Is 1 less than 3? Yes, it is. So I shade the side of the line that includes the point 1, 1, which is the right side. And then I'm just going to darken up where the two shaded regions overlap. So this would be the solution to the system of linear inequalities. Graph each one separately and shade it and see where the two shaded regions overlap. The last few problems are what we would call system of linear equations word problems. So the goal is to set up a system for the situation and then use the methods we've talked about to solve the system. So if you look at number 16, we're talking about investments. So a total of $20,000 is invested in two funds. There's two different funds that paid two different interests. So one paid 6% interest, one paid 7% interest. What we're told is the interest earned was $1,325. The question is how much was invested in each fund. So the idea here is always trying to identify variables for the things we're dealing with. So it doesn't matter what letters you use, A, B, X, Y, M, N, R, T. I usually try and use variables that make sense for the problems, unless we're talking about something like this, where if we're talking about two funds, I'm not going to use F twice. I'm just going to use two different variables. So if I use X, I'm going to have X represent one of my funds, so the amount in, let's call it the 6% fund, and I'll let Y stand for the amount in the 7% fund. The reason we identify variables first is because when we write our equations, then we'll know what we're dealing with, and when we find our solutions, we'll also know what we're dealing with. I really want to see the identification of the variables in your work just because it helps me know what answer goes with what part of the problem. So one equation will be for the total investment. So if I have a certain amount in my 6% fund and a certain amount in my 7% fund, I'd have X plus Y is my total investment, which is 20,000. And then how interest is calculated is it's always a rate as a percent, or excuse me, the percent as a decimal multiplied by the amount in the fund. So what that means, if I want to find the interest I earned from the 6% fund, I would take 0.06, which is 6% as a decimal, times how much that's in that fund, and then I would take 0.07 times what's in my other fund, and then that should equal the interest that I earned from the two accounts together. And then there's an X here. I forgot the X there. So then I have my system of equations that I need to solve, and I have to decide what method is going to be the best. I can try and use linear combinations. I can try and use substitution. I'm not going to graph any of these because then you'd have to mess with the scale and deal with fractions and decimals. It's going to be pretty involved, but I'm going to use, in this case, linear combinations. One thing I like to do first is try and get rid of those decimals as quickly as possible. And the way you do that is if I multiply my bottom equation by 100, what that's going to do is move the decimal place 2 to the right. So what you'll see is I would get 6x plus 7y equals 1,325 times 100, which I'll show you in a second. But at the same time, I'm also going to multiply the top equation by something that would get one of my variables to have the same coefficient. In this case, I'm going to choose 6. So what happens is the top equation becomes 6x plus 6y equals 120,000. And then if I multiply the bottom equation by 100, it just moves the decimal place 2 times to the right. 6x plus 7y is 132,500. So what I have is a system of equations where my x variables have the same coefficient. So if I subtracted, my x's would drop out, and I'd get negative y equals negative 12,500, which means y is going to be 12,500. And remember, y stands for how much was invested in the 7% fund. So now that I know how much is in the 7% fund, I can find how much is in the 6% fund by using my first equation, x plus y, which I'm going to replace with 12,500, and then solve for x, and I should get 7,500. So if you tell me what x and y are, you can write x equals y equals, and I'll know that you have the right values for each variable. We're going to repeat that process for number 17, but now we're dealing with dimes and quarters. So John has 100 total coins, and the coins total up to $22. So if I want to think about setting up a system, I'm first going to identify my variables. So D is going to stand for the number of dimes, and Q is going to stand for the number of quarters. So I should have one equation for the total number of coins, D plus Q is 100, and I should have one equation for how much they're worth. So dimes are worth 10 cents a piece, and quarters are worth 25 cents a piece. So if I do 0.10D plus 0.25Q, that's really finding the value of each coin times the number of coins, should equal how much all the coins are worth. And then I'm going to actually solve this one very similarly to the last one, meaning I'm going to clear my decimals first. So if I multiply the bottom equation by 100, I'm also going to multiply the top equation by 10, because what that'll give me is 10D plus 10Q is 1,000, and the bottom equation becomes 10D plus 25Q is 2,200. So no longer have any decimals, and I made my D variables have the same coefficient. You could have done the same thing with multiplying the top equation by Q, which would have made the Q's match up. That's totally up to you. But now, to get one of the variables to eliminate, I subtract. So 10 minus 25 is negative 15. Please be careful with your negatives. And 1,000 minus 2,200 is negative 1,200. So if I divide both sides by negative 15, I should get 80 for the number of quarters. So if I have 80 quarters and 100 total coins, you might be able to just go directly to the number of dimes, which is 20. And you can check your answer. If there's 20 dimes, 10 cents a piece, that's $2. And 80 quarters at 25 cents a piece, that's $20. $20 and $2 adds to 22. So that solution makes sense for the problem. And then the last problem is another system of equation word problem. We have 6,500 tickets sold, and $45,250 was brought in. There are two different types of tickets, an $8 ticket and a $6.50 ticket, and the question is how many of each kind. So I'm going to set up variables for each ticket. I'm just going to call them A and B. It doesn't matter the variables. A is going to be the $8 tickets, and B is going to be the $6.50 tickets. So I'm going to set up an equation for the total number of tickets, and I'm going to set up an equation for the amount of money brought in. So the system I would set up would be one equation for the total number of tickets, like I said, and one for the amount brought in. So A plus B should be the total number of tickets, 6,500, and 8A plus 650B should be 45,250. The reason that second equation makes sense is $8 per ticket and $6.50 per ticket. You multiply those, should add up to the total number that you brought in, which is 45,250. And then I'm going to solve this. What I'm going to do is use either substitution or linear combinations. I'm going to multiply the top equation by 8. So what that gives me is 8A plus 8B equals 52,000. And then the second equation I'm going to leave alone. So now if I subtract the system, notice 8A and 8A should eliminate. They're gone. What I should get is 150B equals 6750. Divide both sides by 150 using the calculator. I get 4,500. So we sold 4,500 tickets at $6.50 a piece. So to find the number of $8 tickets, you just solve for A in the first equation using 4,500 for B. So A's got to be 2,000. So there are 2,000 $8 tickets and 4,500 $6.50 tickets. Now you added those together, you get 6,500 tickets. If you multiplied each of them by their price, you should get the total receipts. And that's kind of the process of using systems in word problems. First identify the variables, then set up the system, and then decide what method you're going to use to solve it, whichever one makes the most sense for you.